What we're going to look at now is limits in the context of sequences. So we're going to talk about the limit of a sequence. Now, when we say that, when you hear someone say, what is the limit of that sequence? We're talking about the limit as n goes to infinity. Okay? So maybe we'll have the limit as n goes to infinity equals some limit, L. Okay? But it's always going to be the limit as n goes to infinity. Remember, these sequences are discrete. So when we talk about the limit, we're concerning ourselves with what does this function tend to? What are the terms of this sequence tend to as n gets extremely large? Well, to understand what this means, let's go back and remember what the limit of a function is. Like, for example, this one. Let's suppose we've got the limit as x goes to infinity of 100 over x sine x. Now, we know we've investigated functions like this before, and you notice the bottom is x and the top is sine x. The top just oscillates between negative 100 and 100. But the bottom grows without bound. It gets larger and larger and larger. And when that happens, we know that limit is 0. But what does that mean more rigorously? Well, let's look at it here. Here I've got that function graph there. F of x equals 100 over x sine x. And here you see, over here on the right, you see the behavior of the function. It oscillates. And it oscillates, the oscillation gets smaller and smaller and smaller as you go to the right. And you can see, over here, it gets very small. Okay. Now, here's what that means. When we talk about the limit as x goes to infinity, the limit is 0. Here's what we mean. What we mean is if we pick an epsilon and we go above, so 0 is our limit. If we go a little above 0 and a little below 0, like in this case, I went 10 above and 10 below. See, I've got 10 above with the black and 10 below with the red. And notice that in this case, epsilon is equal to 10. We're going 0 plus 10 and 0 minus 10. And we get these two horizontal lines. And notice that every value in the function, as we go out here, is contained between those two horizontal lines. Every value. Now that's for an epsilon of 10. That's when we go 10 above the limit and 10 below the limit. But let's change that a little bit. Let's go down here and change the epsilon and make the epsilon 5. Okay? Now, you notice at this point, there are some values that are not within those lines, right? Like this value up here, this value down here, those are outside those lines. So in other words, the entirety of the function is not between those two lines. However, if you go out far enough, like over here, these values are all between those two lines. And in this case, epsilon is 5. So notice if we go out far enough, yeah, we get everything, the whole value, everything, every function value is between those horizontal lines if we go out far enough on the x-axis. Now let's change epsilon to be maybe 3. Okay. And now notice, yeah, you still have all the function values between those horizontal lines if you go out far enough. You just have to go out a little further this time. Now we could say, well, let's make the epsilon even smaller. Maybe make it 1. And you can see at first the function oscillates outside those horizontal lines. But if you go out far enough, yeah, the function is completely contained between those two horizontal lines. Now, when we talk about the limit being 0, what we mean is no matter what epsilon we choose, we could choose epsilon to be very tiny, 0.001. if we go out far enough on the x-axis, we will come to a point where every function value after that will be contained within those horizontal lines. If we go out far enough, and you can see over here, we've gone out far enough to do it. See? But that's when I chose epsilon to be 1. I could choose epsilon to be 0.00001. And if it's true that for every epsilon we choose, no matter how wee it is, we can find a value way out there on the x-axis so that past that x value, all the function values are contained within those two horizontal lines. Now you might say, well, okay, that's not a sequence though. So we've got here something that's not a sequence. Well, let's go back and I'll move my epsilons back to 7. Let's say. And let's suppose that I want to not deal with the function 100 over x sine x. Let's suppose I want to limit the domain just to the uh, positive integers. Okay, so that's what I'm going to do here. I'm just going to limit the domain to the positive integers. Okay, now, so there I've generated a few of them, and let me turn off the function. Okay, so there they are. But the point is, notice if we do limit the domain to just the positive integers, every value is still on that line, still on that curve. You can see all those green dots there. They're not, they're part of the graph. I'm just taking off everything that's not a positive integer. Okay, but you notice the sequence is going to be on this graph. So if we say that the limit of this 100 over x sine x is 0, then the limit of 100 over n sine n must also be 0. In other words, what I'm saying is, if we're talking about finding the limit as n goes to infinity of some sequence, then you can go back and find the function and just analyze the function and calculate the limit there. So let me show you what I'm talking about. We've got this situation. Let's suppose we've got the limit as n goes to infinity of 2n plus 3 over 5n plus 4. And we want to find that limit, the limit of that sequence. Well, all we have to do is think about the function associated with that. In other words, think about, do we know how to find the limit of this thing? The limit as x goes to infinity of 2x plus 3. Whatever this limit is, that's the same limit. Okay, so I could just find this limit. And you could use L'Hopital's rule on this if you wanted to. L'Hopital's rule, let's see, you don't have to on something like this, but L'Hopital's rule says that this limit is the same as the derivative of the top of the derivative of the bottom. And well, that's just 2/5. So the limit is 2/5. And like I say, you don't have to use L'Hopital's rule on that, but in this case, you could. Okay, so this limit is 2/5. So what I'm saying is, when it comes to finding the limit of these things, a lot of times you can just go back to the function and look at the function associated with it. In other words, when I say the function, I'm talking about replacing the n's with x's and say, okay, the domain is the real numbers. Of course, this domain wouldn't be all the real numbers because you would have to exclude -4/5. But anyway, as x goes to infinity, it doesn't matter. Okay, so when we talk about limits, that's what we're talking about. When we talk about the limit of a sequence, that's what we're talking about. So let's look at some examples here. Let's suppose that we have a sub n is equal to, let's say 5n over e to the 4x, something like that. And we want to find the limit of that sequence. So here we go. We've got the limit as n goes to infinity of 5n over e to the Whoops, this should be n. Okay, sorry about that. E to the 4n. Okay, so let's suppose we want to evaluate that limit. Now, one of the things we can do is we can say, well, I want to look at the function, the continuous function, 5x over e to the 4x. And I want to take that limit. So as x goes to infinity. Now, you might say, well, I still don't know what that is. How do we determine that? Or you might be able to look at it and say, well, you've got this exponential function in the bottom and some linear function up top. Obviously, that limit is 0. But if you didn't see that, one of the things you can tell is that the limit of the top is infinity and the limit of the bottom is infinity. So you have this situation where you have infinity over infinity, and you can use L'Hopital's rule. So let's use L'Hopital's rule. We've got the limit as x goes to infinity of 5 over the derivative of the bottom is 4e to the 4x. Now, if you let x go to infinity, it's very clear. You've got this constant up top and this exponential function on the bottom. Well, it's very clear that limit is 0. So we would say, okay, well, then this limit is 0. Okay, let's look at another one. Let's suppose that we've got the limit, okay, the limit as n goes to infinity of, let's say, 2 to the n over 2x minus 1, or 2, I'm sorry, 2n minus 1. Okay. We want to figure out, well, what is that limit? So what we can do is we can talk about this limit. The limit as x goes to infinity of 2 to the x over 2x minus 1. Okay, so we've got this function. Now, we can use L'Hopital's rule on this. So, because we've got infinity over infinity, just like the case before, but we've got the limit as x goes to infinity of log 2 times 2 to the x. And down here, this is just 2. Okay. Now, here you can see clearly there's no x on the bottom. Up top, you've got this exponential function. So this thing is going to be infinity. So you have this situation where the function, this sequence right here, is just getting bigger and bigger and bigger. No matter how big of a sequence value you find, if you go out far enough, you can find a bigger sequence value. In other words, if n equals 100 gives you this huge sequence value, then if you go out a little further, you get a bigger value. So it just keeps getting bigger and bigger and bigger. When that happens, in this case, we say the limit is infinity. You could say, well, this equals infinity. Or when this happens, you say it diverges. Okay, so this sequence right here diverges. It gets larger and larger and larger. You give me a value for that sequence, and I can go out far enough and find you an n so that you get even a bigger sequence value. It just keeps getting larger and larger and larger. So here's the case where we say, okay, this sequence diverges. So what's going to happen when we talk about limits of sequences, we're going to find the limit, and it's going to be a number, or we're going to find a situation like this where it blows up to infinity and we're going to say, okay, it diverges.